Pete's asked me to come talk about PCA, and really this is about, I guess, what is PCA, and what's the intuition behind PCA? Because I think the impression I get is the way it's approached is quite mathsy, and I think having some of the intuition behind it really helps in understanding. So I'll just jump straight in. So what is PCA? PCA stands for Principal Component Analysis, and what I mean by that is if you have a data set, so say I'm looking at houses, right? I'm trying to estimate the price of the house, but I'm also looking at all the variables. I'm looking at like the length, I don't know, the height of the house, how many rooms it has, you know, how many bathrooms, etc. And I might have a huge data set with maybe like 100 different variables or 1,000 different variables, right? And so what PCA tries to do is well, okay, so firstly, what's wrong with having a huge data set? Okay, so say I'm trying to do linear regression on this data set, right? Then I might say, well, I'll take all this data and represent it as like a giant matrix, X, which you usually call your design matrix, right? So what's wrong with just having like a giant matrix like that? It turns out that when you're doing things like regression, you often have to find like matrix inverses, right? And that's actually quite a costly operation, even for a computer to do, is to find the matrix inverse. And it turns out that if the size of your matrix is n by n, then to do a matrix inverse, it takes time n cubed. Oh. So the point of PCA is saying, well, if I can half the number of variables I'm looking at, then that's like 2 times 2 times 2, which is an 8 times reduction in the length of time it takes me to do this analysis, which is like a whole order of magnitude, so it's pretty significant. So things like, for example, well, if I take the length times the height, or the length times the width, maybe, that's just the area of the house. So maybe I don't need 2 variables, maybe I only need 1, which is the area, right? Or maybe it turns out that even if it's like 9 bathrooms, 5 bathrooms, 1 bathroom, maybe it turns out that this doesn't actually make much difference to the price. So we can just completely ignore this one. So you can see how we're already going from like 4 variables down to 2 there, right? And what PCA tries to do is do this automatically, get the computer to figure this out for you. So if you've got a huge data set, you don't have to use your intuition, i.e. artificial intelligence is figuring out what's most important about your data, right? And which variables should you be looking at when you're doing your analysis. Okay, now I'm going to control Z. Yeah, it works, look at that, cool. Yeah. Okay. Oh no, I've run out of control Zs.
Make these size bigger. See the size do
make it huge. How many at a time? Good.
we need a better backfill solution. Whiteboard solution.
Press Control N.
Can't you just scroll down on the page?
Ah, okay, okay.
All that.
So where do I start with this? Where do I start?
It's a vector.
You need to change back to a pen, by the way.
Yeah. So let's start with. So what I'm going to do is show you. So yeah, it turns out that so Pete came to me one day and he said, yeah, so I've been told that to do PCA, what you do is you find the covariance. Oh, what's that?
Just a thinner brush.
Oh, where's the pen? No,
you want size?
He said, it turns out if you find the covariance matrix of your design function, and then you take it turns out you have to take the eigenvectors, or you have to do an eigen decomposition of this matrix, and then that gives you the principal components and the relative importance of them. And Pete was just like, what the hell does that mean? And so I think what I'm going to do then is I think that's the way that this is sometimes taught, is like here's some algorithm you do to do this. But there's actually, if you think about linear algebra, there's like a really easy graphical intuition for like what's going on and how it works. So I'll show you that. And so the place to start is really simply how do we represent data graphically, which seems like a really obvious question, but it's not quite so simple. So firstly, what's a vector? Does anyone know what a vector is? Anyone?
It's got a direction and a magnitude.
Yeah, bingo. So a vector is something which has a direction and a magnitude, right? So that's one vector A. This can be another vector B. And the point is they have direction and magnitude. So So a lot of time we think of vectors as being like about like this, though, like 1, 2, right? But ooh, interesting. The back pen works too. This is a representation of a vector, right? So if I want to add up A and B, I don't need to do any of this to add them up. All I do is I say, well, there's A, so I start with there's A, there's B, right? And that's the result, C. So A plus B equals C. That's how I add vectors, right? I don't have to resort to using maths or kind of this representation to do it. And so, but obviously we can't get computers to do this, or this is an easy way for us to understand it. But then how do we? So there's two domains here. There's kind of like the geometrical domain, and then kind of like the numerical domain. So how do we go between these? Well, what we do is we introduce what's called a basis. So if I want to write down this vector A like this, so that I can like compute on it, then how do I do that? Well, I might say that I have this basis. So I might say, I'm going to say there's a y in that direction and an x vector in that direction, right? And then what I would say is, well, A is like 2 lots of x and it's 2 lots of y. Okay, can you see how if I take 2 x's and 2 y's, I get the same as A. I get from here A to B, from here to here, yeah. And so now then what I say is in this basis x y, I can write down A is 2 lots of x and 2 lots of y. And that's pretty much, this is kind of pretty much all the geometries you need to understand the PCA. So, okay, the question then is, well, what has any of this got to do with data? So if you've got data, how does this help us, right? Do I want to introduce anything else? Yeah, okay, so there's one more thing I'll introduce before we move on, which is, how much time have I got?
Sorry, I was just trying to...
18 minutes.
Okay, I've got loads of time. Okay. The other interesting thing is if I've got this vector, so I've got this vector A, I could say, yeah, I'm going to have this basis x, y, which doesn't seem particularly special, and we haven't really, what have we gained? And I could say, well, in that basis, A is 2 lots of x and 2 lots of y, yeah? But then what if I say, actually, there's another basis? So what if I say, well, if I put P there, and I put Q there, yeah? Then it might be that actually A is 1 lot of Q, well, actually, it's 2 lots of Q, yeah? Q, Q, and it's 1 lot of P. So start it here, twice Q and 1 P. So then in this other basis, which is the basis PQ, actually I can write A as 2 lots of Q and 1 lot of P. So can you see that fundamentally we're talking about the same thing? This A exists independently because it's something which has a direction and a length, in this space. But I'm able to write it in different ways depending on how I choose my basis. That's quite fundamental. So when we think about PCA, what we're really doing is thinking, well, this data points exist. These houses actually exist regardless of any kind of mathematical framework. So then what's the best basis to choose? So what are the best set of variables to choose that are going to make my representation really simple? So I'll keep going with this. I'm getting nods, which is good. It means this is making sense, I hope. So, okay, so let's go back to data. So say I'm going to work in 2 dimensions because the board is kind of 2-dimensional and it makes it really easy to intuit what's going on. But the nice thing is that we can do things in 2 dimensions in linear algebra. We can scale it up to like 1,000 and we get all that computation for free, basically. It's nice. So if I look at people and we say we've got people with this age and a certain height, yeah? So this might be data you've collected. And you've got, 5-year-old, 7-year-old, 6-year-old, and 8-year-olds. And their heights are like 1.1, 1.2, 0.9, 1.5 meters, yeah? So this is data, and what we're going to do is we're going to try and represent this geometrically to get some intuition about the data. And usually we do this without thinking about it, but I want us to really think through how this works. So what are we going to do? We're going to say, we're going to say, okay, here's our space. We're going to have one vector, one basis vector like that, which is I'm going to call A. And I'm going to say that age goes in this direction, which is a really weird thing to say, right? Because age is just like this number which is associated with all these people. But I'm going to say, let's say that age goes in that direction. I'm going to say that height goes in this direction. And then I'm going to say, here's person A, here's person B, here's person C, person D. I'm going to say that, I'm going to then say, well, these are all vectors in this space. So I'm going to say person A in the basis that I've just created by saying A goes in that direction, H goes in that direction, is 5, 1.1. Person B is 7, 1.2, etc. Yeah? And so what happens then if now that I've created the space, I can put these vectors in the space, right? So I now have, that's like A, B, C, D, right? And so what I've done really here is something we do all the time without thinking about it, is plot a graph of this data, right? But I'm trying to decompose like what are we actually doing, because fundamentally data is not, this is not geometric data. There's nothing geometric about this. What we've done is we're using a geometric analogy to understand the data. So then we can take this further, and PCA basically takes this analogy further to better understand the data, yeah? So what's something else we can do? So usually when we plot this, we'd actually, usually we do a few things. So we make the axes really long. So rather than saying this is like, age of like 5, and it has to go 5 along, we usually just put all the data inside our axes. And we usually just use crosses as well. So we don't have to draw these vector arrows. But when you see a graph like that, fundamentally what you've done is this, yeah? Okay, so what can we do now that we know that? So say I've plotted my data, H, A. Now I might be thinking, well, what other bases could I use to represent this data? So I've got these people, A, B, C, and D, and I've looked at their height and their age. Yeah, but maybe there's some other variables that I might want to look at, which are going to give me some insight. So what if I were to draw a new basis, which was like that? So I'm going to call this P and Q, yeah? A new basis. And you can see that P is like, I don't know, it's like a fifth of A, and it's, I don't know, a quarter of H, right? And you can do the same thing for Q. So this P and Q basis is, P is like, you could give a name, say it's like foo. It's some other property which is derived from the height and the age, because I can write it like that. And so now I'm going to kind of draw what does this look like in the PQ basis. So if I now put P, I'm just going to rotate it so it's easier to see. What does this data now look like? It now looks like this. Can you guys see that? Yeah. And so what's nice about this is then I can say, okay, how important is Q and how important is P? So you can see that Q doesn't really change much. Actually, all of these people, A, B, C, D, have roughly the same Q. But P seems to split them widely, so they've got like a load of different P, right? So it feels like P is like a really useful variable to describe these people. If I say like someone's P equals 5, that pretty much tells me who they are. So I can say, yeah, their Q, they're there, and it doesn't really matter what their Q is. I kind of identify them quite clearly. And so what I might want to do is say, actually, let's just ignore Q. So now I've got some new data, right? I've got P, Q, which I'm kind of ignoring now. I've got my people. So this P is going from like 10 to like 100 to like 1, like really nice spread. And Q might just be like not very much, it might be like, something like that. So I'm just saying, actually, let's just ignore P. Let's just ignore Q. Yeah? So now we're ignoring Q, and so now we've just got one-dimensional data. And there's P. And I'm going to collapse all these onto the line. So I'm going to just say Q is 0, basically. and here's my data. It's now just one-dimensional. So now instead of having to look at my data in 2 columns, which takes me 8 times as much computing power to process because it's n cubed, I can look at my data in just one column. So when I'm processing this data, I've saved 8 times the computing power. And just, I guess, to convince you guys that this is a good thing to do, I can obviously rewrite these equations. So I've got P equals a fifth of A and a quarter of H. And similarly for Q, I have like, I don't know, a quarter of A and a third of H. So I can rearrange these equations to give me A as a function of P and Q, and H as a function of P and Q, right, as well. So I can, from this data, I can get A and H back. And even if I ignore Q and just say, well, what is A and H based only on P? Let's do that. So A and H, we know that our P direction, is in that direction with respect to A and H, because that's how we drew it in the first place, and that's defined by this. And now our data just looks like this. So it lies along that line. So if you compare these two, see this is people represented by the 2 variables, and people represented by just 1 variable. You can see we haven't really lost that much information. If we're trying to predict someone's height or something like that, for example, actually, as long as we know the P, we can get the height pretty accurately, in the same way that we could here. So even though we're not storing as much data, the information about the people is still there. So we can save a lot of computational time by working on the kind of smaller data set and still get the same answers that we need.
Awesome.
That's cool.
Yeah,
Very
makes a lot of
cool.
sense.
And I guess in a future talk I could talk through the mathematics of how you do this. So this is all geometrical, but really what you've done here is you can use linear algebra to figure out what should the best basis be that's going to represent your data in such a way that you can start discarding some of these dimensions. And it turns out it's actually quite trivial to do with linear algebra, but you have to know some linear algebra. So I can give that talk in the future, perhaps.
Yeah,
That'd be great.
Yes.
yeah.
Yes.